Okay, hello. First test for recording at home. Here is a fact, or here's a exploration of the chain rule. So, we know the chain rule, and we, or at least we have learned that the chain rule says that the derivative of f of g of x is f prime of g of x times g prime of x. But what does this actually mean, or rather, how should we understand this? I think an extended example could help. So I guess I'll do it, well, let's see. Let's consider the following derivative. Suppose that we want to take the derivative of the cube root of 5 sine x plus 8, the cube root of 5 sine x plus 8. And, okay, there's this sort of formula, the chain rule, which will enable us to do this. But to really understand what's going on, let's not look at the general formula for the derivative of this function in general, but let's look for the derivative at a particular place. So suppose we want the derivative at x equals pi. Okay, so let's set this as our goal to figure out what this is. How can we do this? Well, I think for starters, we should try to understand that this is a composite function. So we can create an inner function g. The inner function is the 5 sine x plus 8 function. And of course, we know how to differentiate this function. What is the derivative of this function? Well, it's 5 cosine x. Okay. And we also have the outer function. So the outer function is, let's call it f, is the cube root x function, and we also know how to differentiate that. It's going to be, since that's x to the 1/3, then that's 1/3 x to the negative 2/3, or maybe that's better expressed as 1/3 x to the 2/3. Okay, so all of that is sort of traditional kind of calculus. Sort of formulaic, without really necessarily thinking about what we're doing at all. Okay, so let's take a step back and try to do some thinking about this a little bit. Leaving some space here. Okay, what does this all kind of mean? Well, it means there's this function, the cube root of 5 sine x plus 8, and we want to know the rate at which this function is changing near an input of pi. Well, if you understand composite functions, then you know that we're going to first plug pi into the 5 sine x plus 8 function, and then that output gets plugged into the cube root function. And so the story of the derivative of this function, or the story of how fast this function is changing near pi, should begin with the inner function. And as we have seen with the chain rule, we want to investigate how fast this inner function is changing near pi. Okay, so let's make a picture of that. And, well, we should just graph the 5 sine x plus 8 function. So now let's consider y equals 5 sine x plus 8. And where should we be looking at 5 sine x plus 8? Well, at pi, of course. Alright, so we can make a picture of this 5 sine x plus 8 function. It's going to be just like a normal sine function, but with an amplitude of 5, and the whole thing is going to be moved up 8. So if that's 8, and the amplitude is 5, then we're going to go up as high as 13 and as low as 3. And so this means we can graph this function. And okay, based on our understanding of sine, oh man, so that's like pi right there. In fact, in class, the way we discovered what the derivative of sine was for the first time is by sort of drawing these slopes. And, well, we can do that now if normal sine function would have a slope of -1 here, then the sine function, which has been stretched out by a factor of 5 vertically, is instead going to have a slope of -5. Okay, so that's a sort of a geometric understanding of what's happening to the 5 sine x plus 8 function near the input of pi. And of course that is borne out over here by our kind of rules and formulaic approach, because my inner function is 5 sine x plus 8. We differentiated using the rule, we got 5 cosine x, and then when we specifically look at the derivative at pi, cosine pi is -1, so we get -5. So it's all sort of making sense. But I want to think a little bit more geometrically about what's going on here. If this is -5, what we really mean by that is if we zoom in on some tiny little bit of this function, what we're going to get is a delta x and a certain delta y. And by saying that the slope of the tangent line to the curve there is -5, what we really mean is that the ratio between the change in the function and the change in the input near x equals pi is -5, which is to say that, and maybe now is the time to write this, that so I'll write this here. For y equals 5 sine x plus 8, the change in y over the change in, I'll put near x equals pi, this is true, that the ratio between the change in this function and the change in the input is -5, which really should be thought of as saying that the change in this function is just, the change in the output of this function is -5 times the change in the input. Which is to say that this little delta y here is roughly going to be, and I'll try to squeeze this in, -5 times as much as the change in x. And actually, perhaps this is the best way of thinking about what taking the derivative tells us, and this is the best way of seeing this on the picture. It's actually a little unclear on this picture. Maybe I just erase that and I'll just write in that if that's delta x, then we should be thinking about the change in y of this function as being -5 times as much as that. Or we go down by a -5. This triangle is in a 5-to-1 ratio. Okay, so what? Well, now a couple of things now become obvious when you work through one example slowly like this. First of all, though I am looking near y equals 5 sine x at pi, the answer when I plug pi into this function, sine of pi is 0, so that the output is 8. In other words, this point right here is pi comma 8. And so, as we know, if the output of this function is 8 near x equals pi, then it's 8 which is being plugged into the cube root function. So when I go to finish the story, or continue the story, to look at the next curve, the next curve is going to be the cube root curve. But it's 8 which is going to be plugged into that cube root curve. And thus, when I go to sketch the cube root, I'm going to sketch this cube root function near 8, or rather, I'm going to sketch it everywhere, but I'm going to only care about it near 8. So I have, this is 2, 1, and over here is 8. So I got some kind of thing that looks like this. And it's what this curve is doing near 8 that I should be caring about. And to further clear things up, or try to clear things up, here I have this y equals 5 sine x plus 8 graph that I made. I'm going to think of this as the x-axis, the input axis, and the output axis is y. But since this is a composite function, it's the output of the inner function which becomes the input of the outer function. In other words, if I'm plugging in x values initially and I get y values out, then those same y values that come out of the 5 sine x function are the things that are getting plugged into the cube root function. And so I'm going to call this horizontal axis, the input axis, in my outer function y, and I'll call the output of that z. In other words, let me just call, for clarity, this curve z equals cube root y. Just to stress that, okay, I'm kind of repeating myself here, but x values go into 5 sine x plus 8, y values come out, and then those same y values go into the cube root function, and let's just call it z values come out. And I think this is meant to address why, I'm trying to explain why it's, of course, the derivative of the outer function evaluated at the inner function that is important. You would not, it would be silly and wrong to think that we cared about what this cube root curve is doing at pi. We don't care what this cube root curve is doing at pi. We care what this cube root curve is doing at 8. Because near 8, since the output of the inner function is 8, it's the behavior of this near 8 that is relevant. Okay, and now what is it that we would like to now know about this? What we would like to know is what the slope of the tangent line is to this curve at 8, 2. And, well, I don't know what that is, and unlike before, I can't even sort of conjecture it geometrically. I have to do some math to find out. And, okay, well, we have a rule for taking the derivative of the cube root function over here. We have already computed it using that rule, and we got a formula. And I'm interested in f prime of 8, and when I plug in 8 here, I get 1/12. Okay, that is the only real way to determine that, in fact, the slope of this line is 1/12, which looks about right. And which tells me, geometrically, that for every change in x, no, I should call it change in y, I guess, that my change in z is going to be about 1/12 of that change in y. And this looks about right, so I'll erase that delta z, and I'll write 1/12 delta y. Hopefully that's clear. Okay, in other words, to this picture I think explains what's going on, but let's just summarize it in our language over here. What we have just found is that for the curve z equals cube root y, near y equals 8, that the change in y over the change in z, which is just another way of saying the slope of the tangent line, is 1/12. And phrasing that, or rephrasing that slightly, what we have, or what we really want to say, this I got wrong, sorry, change in z over the change in y, is 1/12, and is what I meant to say. The change in the function with respect to the change in the input is 1/12. That's what it means for the slope of that tangent line to be 1/12. Then, what that's really telling me is that delta z is just going to be 1/12 of that delta y. That's what's on my picture. Okay. Well, this way of thinking about the chain rule makes it just extremely obvious what to say overall. What was the overall thing that I was trying to even determine when I wanted the derivative of this function at pi? Well, the thing I was really asking is, how fast is this function increasing near x equals pi? But how fast is this function increasing with respect to x? That's what it means to take the derivative with respect to x. We're answering the question, if you change x a tiny bit, what happens to the overall function? In other words, the very thing that I wanted, was to know what is delta z delta x. This is the question I set out to answer 10 minutes ago. If you change x by a tiny bit, how does the entire function respond? And the answer now is obvious, because, well, I can just compute delta z. What is delta z? It's 1/12 delta y, and delta y is itself, just doing substitutions now, -5 delta x. And so delta z is just 1/12 times negative 5 times delta x. And I conclude that delta z, delta x, is negative 5/12, which is the correct answer. And more broadly, what I have determined is that in general, delta z, delta x, the very thing I am trying to calculate when I am trying to differentiate a composite function, is just going to be, and now following what's going on, I first calculate delta y, delta x, the rate of change of the inner function with respect to a small change in the input, and I then calculate, when I take my second slope, delta z, delta y, which we found here was 1/12. And of course you multiply them because they're just fractions. This is not a proof of the chain rule, this is a way of understanding the chain rule. And it does really make it trivial because it says that, that derivatives are just fractions. Okay, good. My last thing to say, I think this was clear but not a very efficient explanation. Over here in my conclusion, I would like to say that this way of thinking about the chain rule is actually very useful for applications to kind of be comfortable with it here in the Leibniz notation like that. And one sort of, you might think of it as dumbed down, but in some ways it's the deepest way of thinking about the chain rule. What it says is that the derivative of some function with respect to x, and now I'm just changing my notation slightly, but it's really all the same thing, that the derivative of z with respect to x is just the derivative of z with respect to y times the derivative of y with respect to x. And you should be comfortable with this notation, and you should see the connection between the normal way of stating the chain rule, which I think is best for performing the computations, and this more sort of casual geometric way of thinking about the fact that derivatives are just slopes, and they're both sort of saying the same thing. Okay, this was a brief lesson that I gave to, I believe, periods 3 and 4, but not period 6, in the last week of school. And there is a very short follow-up to this, which I will do now.